Software development for real-time embedded systems. Project 8. Hoot hoot.
Welcome to the demonstration of Project 8 for the Johns Hopkins Embedded Systems course. I'm Daniel, and Brad will be our pilot today, as we show off a quadcopter-mounted IMU module capturing roll, pitch, and yaw, transmitting values over I2C to an Arduino Uno, which formats and reports the results in degrees to a Raspberry Pi over USB, and ultimately transfers the IMU data to my host machine via Wi-Fi. We're still running with the KK controller quadcopter design from Project 4, and the enclosed Raspberry Pi 4 with portable battery pack tied to the undercarriage as in Project 6. This time, the Adafruit absolute orientation sensor is affixed to the front, albeit MacGyvered on with zip ties for the time being. As before, the Pi has the 32-bit Raspberry Pi desktop OS loaded onto an 8GB SD card and Wi-Fi connected to a local router. The Arduino is running a sketch that leverages free RTOS libraries to define and enforce a real-time task that reads in values from the Adafruit peripheral. It also includes the Adafruit sensor libraries to parse results, and a library for streamlined I2C setup. The Arduino code is very simple, setting up the serial connection and creating the single RTOS task. With nothing prioritized higher, the task runs continuously, receiving orientation data from the Adafruit sensor using their library function, then outputting formatted values as text over the serial bus. It delays 150 milliseconds before proceeding with the next read. The background of the video is my Windows 10 desktop, but I have an Ubuntu VM loaded through VirtualBox to make the host connections later on a little more clean. Overlaid on the left will be video captured during the demonstration from an iPhone, but there may be some desynchronization between the recordings. What you just saw was me using PuTTY to SSH into the Raspberry Pi over Wi-Fi from my desktop, and then running the LSUSB command to verify that the Arduino was connected. We saw the device was on ACM0, so I ran a cat command on dev/tty acm0 to display a live feed of the data being reported over that serial bus. You can see here the data is coming in formatted yaw, pitch, roll to show the orientation on the X, Y, and Z axes in degrees with 4 digits to the right of the decimal place. The quadcopter is restricted from making any really dramatic moves here, but I used the cursor to highlight a couple moments where it had some notable changes. However, I don't have high confidence that the iPhone video and the screen recording are synced one-to-one. After killing that, the second demonstration is running the same cat command, but this time piping its output from standard out onto the Raspberry Pi's port 4000 using netcat. Then on my Ubuntu VM, I run telnet, providing the Raspberry Pi's IP and port to complete the TCP connection. And lo and behold, it looks the same as the cat command from before, but this time it's a direct IP connection instead of having to SSH in. In that vein, the third example is just another method of receipt for the same process. I leverage netcat the same way on the Pi, but on my VM I open up Firefox and direct my web browser to the IP and port, allowing me to see the data outside of a terminal. But it lacks the native ability to auto-scroll to the bottom like the terminal does, so it's a little less useful in practice. And the final delivery method will be using the remote desktop VNC viewer, logging into the full graphical interface of the Pi over my desktop, where I've installed the Arduino program, and once I select the proper serial port, I can open up the Arduino serial monitor, which once again shows us the same roll, pitch, and yaw data. And that is the long and short of this IMU demonstration, so thank you for watching. See you in Project 9.